Hello, welcome to a very special edition of a CNA's Opus. My name is Rich. I'm a certified nursing assistant. And first, I want to start this off with a little story. Uh, just a couple days ago, I was out talking to this woman, and it turned out she was a medical doctor. I was talking to her, and I asked her if she wanted to have a drink. Now, I understand that there's a big social economical gap right there. I said, listen, I can close that gap. I can close that gap. What I'll do is I'll run 22 miles in the rain here in your honor if you go for one drink with me. And not only did I run, I didn't build up to it either. Not only did I run 22 miles in the pouring rain, I ran 26, and I didn't build up to it. I normally build up. I was running like 12 miles here and there sporadically. I ran 26. My ACL was hurting so bad. My back, everything was in pain. And by the time I was done, it was like hours later. She was gone. She was gone. And I was soaked and serious freaking pain, right? And I think I'm owed a drink there still. If that woman ever watches this video and recognizes me, I'm owed a drink on that. It's 26 miles in rain. I'm owed a drink on that. Anyway, what I want to talk about right now is folic acid and the conversion of uracil to thymine, which is kind of there's actually, well, I'll get there in a second. So right here you have folic acid, which is over here is glutamic acid attached to tauroic acid. So the glutamic acid right here, there's 7-chain carbon right here. There's a carboxylic acid group right here, carboxylic acid group right here, and there's your amino group right there written as a residue because it's going to attach to this, the tauroic acid, and the P is silent right there. And right here this is a pyrimidine ring. It's modified because it doesn't have the double bond right there, top, because you have a double bond to an oxygen right there. So that compensates for that. Down here you have an amino group right here off of this carbon, and that's a pyrazine ring right there. This second ring right here, and there's a benzene ring right up here. So let me just go to a better diagram and show you what's going down. This right here is the whole chain of folic acid. Put it on this side. Let me just show you a little better. That right there is the whole chain of folic acid. And the enzyme that's going to work on the first two reactions is called dehydrofolate reductase. And folic acid, by the way, is very important with spina bifida, and in pregnant women. Commonly, women will take folic acid because there was a link between that at low folic acid levels and spina bifida, and glutamic acid, which is attached to the tauroic acid, has its own role, and that is it can act as an excitatory neurotransmitter in the brain, which can be looked at for like ADHD. However, like there's been supplements. They're not really supplements. They're basically drugs that are sold over the counter. Somebody took paracetam and made it like 1,000 times more potent, which has an effect on glutamic acid in the brain, which again is an excitatory neurotransmitter. Wakes you up, gets you going, but it's non-stimulant, so it doesn't constrict the blood vessels, it doesn't raise the heart rate or anything like that. However, there can be a lot of interactions, things like that. So I would say do not take anything like that unless you're under the guidance of a medical doctor, because there could be interactions and serious side effects to it. So don't take anything like that. unless you are under the guidance of a medical doctor. That being said, about glutamic acid and folic acid, this over here is the teroic acid, where the P is silent. The first two reactions right here is dihydrofolate reductase, and that the first reaction is it cuts off this double bond right here in red. That's the first reaction. It cuts off that double bond right there, and there'll be an electron that will go back to the nitrogen and an electron that will go back to the carbon. So there'll be unpaired electrons right there. So it'll add a hydrogen right here on the nitrogen and two hydrogens on the carbon right here. So carbon is satisfied because it has 4 links, 1, 2, 3, 4, and nitrogen is satisfied because it has 3 links, 1, 2, 3. Then the second reaction of dihydrofolate reductase is that it cuts this bond right up here, and it adds 1 hydrogen to this carbon here, which satisfies it because it has 4 links right now, 1, 2, 3, 4, and it adds 1 hydrogen to this nitrogen up here. Then it goes down here. This is tetrahydrofolate. So the tetrahydrofolate, again, thymidylate synthetase comes in and chops off this hydrogen and this hydrogen right here, and a carbon comes in. And again, a carbon wants 4 links to it. So an electron goes back to this hydrogen, electron goes back to this hydrogen, electron goes back to this nitrogen and to this nitrogen. So you have unpaired electrons there. So the carbon comes in and it gets its 4 bonds right there. This is just cut off. Carbon comes in and it gets these 4 bonds. Well, 2 from the hydrogen and 2 from the nitrogen right there. So it makes this like V shape right here. Now, thymidylate synthetase comes in at this step, which is N5 N10 methylene tetrahydrofolate, and chops this off right here. It has this and this. So now you have a carbon attached with 2 hydrogens. Let me just write that down because that's going to be important right here. Carbon, 2 hydrogens. So that's a methylene group right there. So this methylene group right here, this carbon and 2 hydrogens. In uracil, uracil has a carbon with 1 hydrogen attached, and this thymidylate synthetase will go in there and chop that hydrogen off the uracil, and this right here, this methylene group, will slide right in there where that hydrogen was chopped off that carbon at the uracil. So if I could just, in red, just put that right there. This is the hydrogen that was chopped off of the uracil right there, right? And this methylene group comes in there and kind of slides right in there, and this hydrogen that was chopped off reattaches to the carbon. And this methylene group right here came from this N5, N10 methylene tetrafolate, which was basically a modified folic acid, just a series of reactions in the body that got to this. So it was actually folic acid finally got to this. This portion right here came from the folic acid. Got chopped off right there. And this got chopped off of the by thymidylate synthetase is the enzyme that's doing these last reactions right here. Takes that off. Took this off the uracil, and then it recombines right there, and then it recombines back. Let me just put it right back in there. Back to the uracil. So that got cut off. This slides in, and then it reattaches to the uracil. So now the carbon has 4 links to it, which carbon wants 4 links. 1, 2, 3, 4. To the uracil. Now uracil becomes thymine. And thymine is DNA. Uracil is RNA. The other difference between uracil and thymine is that uracil, it's RNA, but it's attached to ribose. And ribose has an alcohol group on the second carbon. And one of the reasons it has an alcohol group on the second carbon is because when you make messenger RNA and it goes out in the cytoplasm of the cell, you don't want it continuously going to the anticodon within the ribosome and continuously making that amino acid, because it'd be an overexpression of that amino acid or that protein. So you want that messenger RNA to decay, do its job, and then be decayed. And one of the ways it does that is that, if I could just draw this right out here, if you're looking at the ribose sugar there, hold on one second, and there. So if you're looking at a ribose sugar right here, right, that'll be RNA. That would be attached to uracil, right? This one right here off the second carbon makes it reactive. That alcohol group, that hydroxyl group right there, is highly reactive. So it's one of the ways that RNA gets destroyed once its job is done. So it doesn't overexpress any protein. And deoxyribose, that one off the second carbon, is gone. So this alcohol group right here is to help make the phosphosugar backbone, and it's kind of quarantined, so it doesn't react. It just makes bonds here for the sugar phosphate backbone of the double helix. This one over here will be reactive. You want the DNA conserved. You don't want your DNA being destroyed constantly. So that alcohol group off the second carbon is not there, and that's the major reason why. The alcohol off the second carbon in RNA, particularly messenger RNA, you want the messenger RNA to be destroyed at some point once it's done with its job. And one of the ways it does that is has the alcohol group off the second carbon. So basically, just to recap here, the folic acid goes through a series of reactions, which gives a methylene group right here, and that's from thymidylate synthetase right there, and that'll go down to uracil, and thymidylate synthetase cuts off that hydrogen from the carbon, and that comes in there, and now it has 4 bonds, and that makes thymine, which is attached to this right here, the deoxyribose, which has only 1 alcohol group off it, off the third carbon, and not off the second. When it's off the second, that's RNA. So it's this uracil to thymine is basically this off the second carbon is gone, and this is added, the thymine, and that makes thymine from uracil. There's actually drugs, old chemotherapy drugs, that will block the action of thymidylate synthetase, which are older chemotherapy drugs, which I may do eventually at some point in one of these videos. It doesn't completely blow your mind. And that's it. Right, CNA. See you later.